Good morning, everybody. Welcome to this 3 lecture module on cement production, composition and chemistry. Now, typically if you look at concrete technology courses that are offered in different curricula, the coverage on cement is restricted to understanding the physical properties of cement, some ideas of chemical composition, and overall just an idea about how cement is actually tested from a quality control point of view. However, if you really look at it, much of what concrete performance is all about is the way that cement actually interacts with water, hydrates and fills up the microstructure. So there's a lot of inputs that have to go into really understanding what are the aspects of cement which really affect the properties of concrete. And if you really look at it, overall the performance of concrete depends a lot on how cement has reacted with water, how cement has reacted with other admixtures and other chemicals that you add in the concrete and so on. So in this three lecture module, we'll look first at some aspects of cement production, and then we'll talk about the composition as to how the production leads to a specific class of compounds to be formed within cement, and then finally we'll look at how these compounds actually interact with water to give you your regular cement paste which binds the aggregates together in the microstructure to form concrete. Okay, so let's get started first with cement production. So you all know that in the past several different types of binders have been used, and one of the most commonly used binders is lime. Okay, different forms of lime were used in binding mortars which put together different blocks of stone or brick and made masonry structures possible in the past. In several cases, lime was also used as an ingredient and a binder for concrete, and there are a lot of past examples from history where lime has been used as a binder even in concrete. Now, you might have heard of the term pozzolanic material like fly ash or slag or silica fume. So sometimes you may see that in the past several of the lime mortars also made use of pozzolanic materials, and sometimes the use of these materials was inadvertent. That means people were not really knowing what they were doing, but they just thought that okay, if you added this particular ingredient to the lime mortar, it gave it very interesting properties. Some examples of this, for example, are the use of volcanic ash in Europe. Several instances are there of Roman and Greek structures that were built with different types of volcanic ash mixed with lime, and that seemed to give very interesting properties to the lime mortar. In India also, there's been a lot of use of pozzolanic materials. One primary material that has been used in the past, maybe thousands of years ago, is surki, which is basically ground brick that is ground into a powder. So you get this fine ground brick, and that is mixed with lime, and it produces very interesting properties to the lime mortar also. So again, these are examples of pozzolanic materials that were used in the past. Today, of course, our definition of pozzolans has changed a lot. We have been using several artificial materials rather than naturally occurring materials as pozzolanic materials, but we'll talk more about that perhaps later when we talk about different types of blended cements. Now, one more binding material that was used in the past was bitumen, but today, of course, bitumen is restricted entirely to the manufacturing of roads, uh, flexible pavements primarily. Okay, so now how did modern cement get developed? One of the names that comes in the history of cement development is John Smeaton. Now, interestingly, John Smeaton was apparently the first civil engineer. Now, I know that many of you may not be aware of this, but building prior to John Smeaton's construction projects, building was essentially taken care of by the army or the military. So he was the first person outside of the army or military to take up building construction, and so that's why he was called the father of civil engineering. He was the first civil engineer, and interestingly, his name also comes in the one of the first sort of cements that was actually used. So while planning the building of this lighthouse tower in the UK in 1756, he found by accident again that the best limes that were used for mortar had a very high degree of clayey matter. That means there were impurities present in the lime that made it very interesting and interactive with water and gave very interesting properties to the lime mortar, improved the binding capacity and so on. Now, so what he did ultimately was used this kind of an impure lime along with the pozzolanic material in equal quantities, and this led to the construction of this monument called the Eddystone Lighthouse Tower. Uh, of course, this was constructed in 1759, but of course now it's not no longer in service. It was shifted brick by brick to a different location, but it is still a major national landmark because it was one of the structures which was first built by a non-military person. All right, one more name that you may have heard of is YCAT. Many of you might have tested cement in the lab, and one of the common apparatuses that we typically use in the lab is the YCAT apparatus, right? You must have known of the YCAT apparatus. We use it for testing normal consistency and setting time of the cement, and we establish how much water is actually required by the cement to get it to a certain workable consistency. So YCAT was one of the principal scientists as far as cement is concerned. So he was the first one to actually prepare an artificial hydraulic lime by calcining or burning an intimate mixture of limestone and clay. So truly speaking, that's how cement is also manufactured. But until that time, people were simply adding this lime or impure form of lime and expecting it to perform well without really understanding the reactions that take place between the lime and clay itself. But probably the first person to do this actively was LJ Vicat. He was a French scientist. Now, in the stages of cement development, people have looked at different types of cement that have been there over the ages. So today, of course, we call it normal Portland cement, but earlier varieties of the same were called proto Portland cement or meso Portland cement, depending upon which stage we are actually looking at the development of cement at. Now, one name you might have heard again is Joseph Aspdin. In 1824, he basically obtained a patent for his cement. So again, until that time, people were preparing these mixtures of lime and clay and burning them together to get the cementitious properties. But Aspdin probably was the first one to patent it, and he termed it as Portland cement. Now that is something interesting because even today we call our cement as Portland cement. If you really look at it, this patent was obtained in 1824 and it should have run out years ago. But such is the power of the brand name that even today we call it Portland cement. Actually, the Portland term does not have any significance today. He simply named it Portland cement because when he saw that when it reacted with water and set and hardened, it looked very similar to a typical limestone that was found in the region from where he was from. That's why he called it Portland cement. Okay. And later, of course, the development of cement was taken up by his son, William Aspdin. And of course, the cement also changed nature a bit. The technology for cement manufacture improved after that, and we go into the category of what is known as meso Portland cement. But today, of course, the technology is much different. So scientists wanted to find out what was the difference between the cement that was produced in the kiln that was used by Aspdin, whereas as compared to what we produce in normal rotary kilns in modern cement plants. So let's take a look at how this was done. So this is an example of a kiln that was used for burning by William Aspdin, and on the right side you actually see an image of the cement that was actually produced in this kiln, which people actually removed with the help of by scraping off some material from the kiln floor. And you can see here very clearly, this is actually a microstructural image, microscopic picture. You can see different types of ingredients here. You see the larger grains which have been marked as A, and these larger grains are those of A-lite or C3S, tricalcium silicate. The smaller grains are those of B-lite. Now this is similar to what you would find in normal Portland cement also, but to some extent the sizes of the crystals that have been forming and their reactivities are quite different. What are the differences principally? Let's take a look at some of these. So if you look at the clinker that was prepared by Aspdin, the relative burning rate of the clinker would have been quite slow. If you have seen some of these kilns that are used for brick manufacture in the rural areas, you see that these are mostly of the vertical type. So the material that is used for construction or for preparing the brick is charged into the kiln, and then you have the heating source from below, and then ultimately once the heating is completed or burning is completed, you then retrieve the material, take it out, and that's your cement. So in modern kilns, of course, we use a rotary kiln. The rotary kiln, you feed the material at one end and it simply rotates in the kiln and comes out at the other end. So that's basically ensuring that you have almost a continuous process of manufacture. So as a result, the modern clinker has a relatively quick burning rate. It spends time in the kiln only for about 30 minutes, whereas in the old times the clinker would have spent as long as it could possibly, based on when they actually removed the material. So as a result of this, the kind of crystals that you form of C3S and C2S could be quite different. For example, the alite or C3S size could be was probably about 60 microns in the old clinker, whereas today you find most of the alite crystals are of 10 to 15 micron size. Overall range varies between 10 to 40 microns. B-lite on the other hand is a lot bigger today as it was before. The cooling rate, the rate at which the material that comes out of the kiln is cooled, was very slow in the previous days because there was no artificial system of cooling. People just removed the material from the kiln and expected it to cool to room temperature. But today, of course, when the material comes out of the kiln, we actually have several systems to actually cool it together, cool it and get a very unique sort of a consistency with the product. There are different forms of C2S or dicalcium silicate which were not formed in the previous kilns, but today we actually see it. And of course, the kiln that was used in the past was vertical or beehive type kilns, but modern kilns today are rotary kilns. Okay, so now let's look at how cement is manufactured in modern plants. You have to keep in mind that cement is a very unusual industrial product. It is produced in very large quantities. In case you didn't know, in the year 2014 or 20 and also in 2015, the amount of cement that was produced across the world was 4,000 million tons. So very large quantities of cement, and of course these are produced in plants that can almost produce nothing else because the cement plants have to be dedicated to produce cement. The product is produced by a combination of several unusual operations which involve mining, very fine scale mixing or blending of raw materials, very high temperature clinkering reactions, controlled cooling, grinding, blending and finally shipping in packaged form under very highly controlled conditions. Now chemical composition, you all ought to know, is maintained within narrow limits because ultimately when the cement goes out to the market, when you buy a bag of cement from the market, you have to be sure of its performance. As a result, when they actually sell the cement, it is sold with a very high degree of control on the chemical composition, otherwise you will not get the right kind of performance. So again, this is done in spite of very large tonnages. I already told you that 4,000 million tons was actually sold as far as cement was concerned in year 2015. Interestingly, of course, India is the second largest producer of cement after China. China was the largest producer and is still the largest producer, but India is expected to overtake the production in the production of cement. It's expected to overtake China by the year 2050, and that time we'll be the people manufacturing the most amount of cement. That is only natural because a lot of projects in India are still coming up, and there's a lot of scope for using concrete. And because you're using concrete, you have to use a lot of cement in it. Now, if you look at the investment required to put up a cement plant, it's upwards of $250 million. It's a very large investment. And of course, in order to ensure that you're able to manage this level of investment, you have to produce continuously. The cement has to be produced continuously to pay off the cost that you've spent in installing this capital expenditure. And the plants also must produce continuously over the day to ensure that you have the integrity of the kiln maintained. What am I talking about there? So supposing you are producing the cement which is coming out of the kiln and you stop the manufacturing of cement for some time. The next batch of material that you put into the kiln will not come out with the same kind of quality, same kind of consistency as the previous batch. So every time that you stop the manufacturing, the quality suffers. So to ensure that you have the same integrity of the product as well as the process maintained, you have to make it run continuously. So people operate at 3 shifts per day, 24 hours a day, 7 days a week. They only shut down probably once a year for maintenance, and without that obviously the cement plant won't work properly. The plant also has to comply with severe environmental constraints because today you know that there's a lot of stringent regulations as far as air pollution is concerned, and while you are manufacturing this kind of a product, you can imagine the kind of gases and dust that go out into the air, and these are very highly controlled. These are regulated by a large extent. For that, the cement plants have to really straighten out their procedures to ensure that the kind of output of these gases and dust are minimized to a large extent. And all this has to be done to produce a product that is cheaper than mineral water, right? We are producing cement primarily at less than 8 rupees, or we are selling cement at less than 8 rupees a kilogram. So truly speaking, if you buy a bottle of mineral water, the minimum cost is about 10. So cement is cheaper than mineral water. It's cheaper than most of the commodities, but of course we need very large quantities of it to do our construction projects. So all this complicated operations are resulting in a material that is fairly cheap and easy to use. Okay. So now let's look at what are the raw materials used for manufacture of cement, and then we'll get along with understanding how the process of production actually takes place. So as far as raw materials are concerned, the principal raw material for cement manufacture is limestone. So ultimately we are still clinging on to the same technology that people used in the past. As I said earlier, lime was the principal binder, then people started using lime with some impurities like clay. Now interestingly, cement is basically lime with a lot of clay impurities, and it produces a very interesting combination of products when it comes out of the kiln after reaction. So the principal source of cement manufacturing is limestone. So all cement plants are located typically next to limestone belts or limestone deposits, because that's where you get maximum quantity of limestone, and then you don't have to really transport it to large distances to really make your cement. So this limestone gives you calcium carbonate, CaCO3, and it also has some impurities like iron and alumina, iron oxide and alumina, which are present within the limestone. The impurities can also include some clay. You all know that clay is basically aluminosilicate, and in most of the cases clay is present already as an impurity, but sometimes you may have to extract additional clay to give you the right quantity of silica and alumina, or SiO2 and Al2O3. Now you all know very well that in the final stages of cement manufacture, we add gypsum or calcium sulfate dihydrate as a set regulator, without which the cement reaction would not happen in a normal way. We will talk about that when we get to the chemistry of cement. And in modern Portland cements, typically we always add some sort of a performance enhancing additive. If you look very carefully at the Indian standard regulations for Portland cement, you'll see that up to 5% of performance enhancer is permitted for cement manufacture, and in most cases the performance enhancer is either ground limestone itself or fly ash. This is done in order to ensure that you don't have a very high clinker component in the cement, so that's environmentally more conscious, and secondly it also reduces the cost of your cement production, because you are adding a material which is not processed directly into the cement manufacture. So we'll get to understand more about this when we understand the final stage of cement manufacture. Now where do these materials come from? Where do these raw materials come from? There are several sources. If you look at calcium or calcium oxide, it comes from limestone, it comes from marl. Now marl is nothing but, you see here there's marl is nothing but limestone with a high fraction of clay minerals. So it's already limestone which is clay as an impurity, so that's marl. And then you have calcite, naturally occurring calcite or aragonite, which are basically calcium carbonate forms. You can also get it from shale, seashells, and sometimes even from the dust that comes out from cement kilns. It's called the cement kiln dust. Okay. Silicon or silicon dioxide is obtained from clay, from marl. Sometimes you may have to add sand, okay, because if you don't have the right quantity of silica, you may have to add sand. Shale, fly ash, rice husk ash, slag, these are all sources of silica that can be added to the manufacture, supposing you don't have sufficient quantity of it coming from the clay. Aluminium or aluminum oxide comes from the clay, shale, fly ash, or sometimes you may have to add aluminum ore like bauxite, not the pure bauxite, but the refuse that comes out of the aluminum ore mining industry. Iron or iron oxide comes from clay, iron ore, mill scale, shale, or blast furnace dust. So all these are components that can be utilized to give the right quantity and the right blend of the oxides that we need to manufacture the cement. Okay, so now how is this process going to happen? How is the cement production actually done once you have these raw materials in place? So let's look at a simple schematic. Now this is a fairly easy diagram to understand, but it's not really presenting the entire scale of complexity that is involved in the process. So I'll just walk you through this diagram. So you have here on the top left of this diagram, you have the limestone quarry. So that's where the limestone is actually extracted and excavated, and then it goes to the grinding operation, because you know that limestone is extracted in as a stone, as large boulders. Now this has to be ground to a very fine size. So for that it goes through crusher and then through a secondary crusher to ensure that you're getting the right sized material. So this is the fine ground limestone that you get. Then it goes into a storage silo, where there are other storage silos for the clay and sand if you need them. For example, if the quantity of the materials required is not sufficient, then you need separate silos for the clay also. And then you do a proportioning, that means you mix it in the required quantities and send it to the grinding mill to ensure that these are blended or mixed properly. Once it goes through the grinding mill, it goes through a set of towers which are called the preheater towers. Okay, the preheater, that means before it goes into the burning in the kiln, it gets heated. Right. Now I'll come to why it's all done after a little while. So the material from the preheater tower comes into the cement kiln or rotary kiln, where it moves by gravity from one end to the other end where the fuel source is located. So you can very clearly imagine that where the fuel source is located, the temperature of the kiln will be the maximum, and at the other end where the material actually comes into the kiln, the temperature will be the lowest as far as the kiln is concerned. Once the material comes out of the kiln, it goes through a process of cooling through this clinker cooler, which is on the bottom left side of your image, and then the material that comes out of the clinker cooler is called the cement clinker. Okay, that's the final manufactured form of clinker, which then gets mixed up with gypsum and any other additives that you might want to add, and in the final stage of cement manufacture, all this is ground together in this grinding mill, which is typically a ball mill, which we use in most cementing plants. This is a ball mill where the material gets ground and then it gets stored and packed in different forms, like in silos, like in bags and things like that. Okay, so you've seen it in several forms, like in bulkers, you see several bags. Most of these bags, cement bags, typically weigh 50 kilograms. Okay, I'll come back to why it is 50 kilograms a little while later, but right now this is how the cement production process is. We'll talk about different steps involved in this process in just a little while. Now this schematic diagram is again depicting the same process in a much easier to understand manner. So you have limestone quarrying followed by crushing and grinding to get the right size material. Then you have two ways of mixing the materials together. One is called the dry process, okay, and one is called the wet process. So we'll again talk about these in more detail in just a little while. With the dry process, typically you also have a preheating, and then the material is sent to the rotary kiln. From the rotary kiln, the material comes out, gets cooled in a clinker cooler, and then the clinker is stored and finally proportioned with other additives like gypsum or fly ash or limestone, as the case may be, and then the cement is produced and to the required degree of fineness and physical and chemical properties, and then it is sent for dispatching. Okay, so I'll just walk you through a typical cement plant that you'll see. Some of you may have visited cement plants, so this may not be new information for you, but I'll just walk you through a cement plant to show you the kind of processes that are taking place in this plant. This is an example of a plant that I had visited in Chhattisgarh. So this is a Lafarge cement plant. You can see here, this is the yard where they stored the limestone. You can see on the right side of this image, you see that there's a heap of limestone which has been stored, and you can also see a large set of conveyor belts all over the place. These conveyor belts are going to take this limestone towards the grinding operation. So you see the conveyor belt now carrying the limestone towards the grinding operation, and so this will go into a grinding unit or a pulverizer where the limestone will be ground to a size which is small enough to mix well with the clay. So now this is the grinder. This is the unit which is grinding your cement and converting it to a very small size. Another picture of a different grinder, because you see there's a crushing equipment is typically separated into different parts. You have a coarse crushing and then you have a fine crushing to ensure that you finally get a very good mix or very good blend with the raw materials. After crushing, it goes into this storage silo, okay, and from this silo it will be proportioned in the right quantities and the material will be sent to the preheater tower. So this is your preheater tower, where the material that is mixed up together, the limestone and clay together, are mixed and then they are sent to this preheater tower. Okay, we will talk about the significance of preheating in just a little bit. Once the material comes into the preheated tower, it goes through a different stacks and finally it ends up in this rotary kiln. Now of course the rotary kiln is not at your front, it's at the back. You can see it here at the back. I'll show you another picture of this. This is your rotary kiln, which does not have a very large slope. It has a very gentle slope, so that the material that comes in at one end gently goes with its own weight, basically without any added pressure. It just goes by its own weight from one end of the kiln to the other end. Okay, that's your rotary kiln. This pipe here that you see, which is of a large size in front of the rotary kiln, this pipe is actually used to carry the heat back into the system. So the heat that is released or heat that is wasted in the process of clinkering, that heat is retaken and sent back into the preheating process so that you can improve the efficiency of the process. Now this is the rotary kiln again from the other end. Okay, so the material comes in at this end and comes out at this end. So you can imagine that the fuel source is located at this end of the rotary kiln, where the maximum temperature will also be felt. This is the end of the rotary kiln. So what I am showing here is actually the fuel source. This end is the fuel source where the maximum temperature is, and the material is actually coming out at this end. And this is the control operation of the cement plant or rotary kiln. In cement plants, everything is highly mechanized and computer controlled. You don't really have any human intervention unless something goes wrong, of course. Most of the processes are well controlled by an interface which is very easy to operate, and quality control also forms a large part of this entire scheme of things. I'll come to that towards the end of this lecture. And so this is the clinker that is actually coming out of the cooling process. You can see here the clinker which is coming out of the cooling process. This clinker is almost looking like nodules. So it doesn't look like a powder. This is because of all the fusion that has taken place inside the rotary kiln and after the cooling process. So you can actually see the clinkers in the form of nodules. Okay, so you can imagine that this has to be actually broken down into a very fine powder to get the typical cement that we are all understanding, or what we typically get in the market. Alright, this is again a picture of the final process of cement manufacture. You can see the storage silos for the cement from which it goes to the packaging, and the packaging is either done in bags or the cement is actually shipped in bulkers. And oh sorry, I missed one step in the process. That was not the packaging silo, that was actually the silo for the clinker, because you know that one more step is there in the cement manufacturing process. The clinker is interground with the gypsum and with other additions in this large cylindrical drum, which is basically the ball mill. So all that is done here is that you put your clinker and all the additives into the ball mill, then you add these large steel balls and this drum rotates. So the steel balls simply crush the clinker and the other additives together. So by impact you are crushing and blending at the same time. So that's very important. You're not only crushing the material to the right size, you're also ensuring that there's a very uniform blend between the cement, clinker, the gypsum and any other additives that you may put in the process. Okay, so these are the processes that are involved in the cement manufacturing. After of course you get the material out of the grinding mill, it goes to storage and finally packaging and shipping. So those are the processes that are involved in cement production. Now before I get to the individual steps in the manufacture and try to give you an example of, or try to give you an understanding of why these processes are important, open the floor for any questions that you might have, because at this stage we are moving into a slightly different scheme of things. We'll get into the specifics of cement production. So before we get into that, please do let me know if you have any questions. Okay, there's a question by one of the people in the audience that when to adopt dry process and wet process. There's another question on what is green concrete. Now of course this is not really part of the lecture that I've given, but I'll answer that anyway. So very many people have different ways of saying what is green concrete. One way to look at green concrete is what is environmentally sustainable. That means concrete that uses materials that really don't put a large burden on the environment. For example, if I replace a large part of my cement with something like fly ash, let's say I use a high volume fly ash concrete, I can call it a green concrete. It's green from the environmentally sustainable point of view. But in different parts of the world, green may have a very different meaning. For example, if you go to the US, green concrete is something that is not set. So that's very interesting. In India, we call green concrete as something that is environmentally sustainable, but in the US, they say green concrete is something that is not set. So again, depends on what you are meaning by the word and where you are in the world. That really helps you understand what this term is all about. Yes, BEC, you wanted to interact and ask some questions?
So what is the binding material used in the stone arches in ancient days?
Okay, okay, the binding material used in the past stone arches. Okay, I understand. Okay, now again, please remember a lot of our ancient monuments are built. So most of the binding material that was used in either stone or brick structures in the past was made with lime and sand mixed together. So you know that lime or calcium carbonate, once it's burnt in kilns, it gives you calcium oxide because the carbon dioxide part gets removed. So once this calcium oxide reacts with water, so when you mix the lime water, you mix a calcium oxide, that is quicklime, you mix water, and then you mix sand, right? So the kind of lime that you get uh, basically reacts with water and forms what is known as calcium hydroxide or Portlandite. So this calcium hydroxide, when it's exposed to the atmosphere, when you have atmospheric carbon dioxide that interacts with calcium hydroxide, it converts that back to calcium carbonate. Okay, so the lime mortar essentially results in a hardened material that is a mixture of sand and calcium carbonate, and that calcium carbonate has been formed from the lime that was initially derived also from limestone. So you actually complete the so-called lime cycle. Okay, so most of the past stone and brick structures were bound together with the help of lime mortar. Okay, now there are some of the questions that people have posted as written questions. So there's a question regarding Surki. Can we use waste bricks? Okay, now again, please remember that Surki is a finely ground brick. Okay, and interestingly, if you make brick properly, that means if you make it with the right temperature of burning and all that, you don't end up with any reactive material. You end up with something which is non-reactive. Okay, but still you can grind it as a powder and use it as an additive in your mortar or concrete. It will help as a filler. But interestingly, when when the brick is not ground properly, when it's not burnt properly, let's say we take the burning temperatures only to 7 to 800 degrees Celsius, when it's not burnt that well, it gives some reactivity also. So when you have a finely ground brick or waste brick that has not been burnt properly, that may actually give you good reactivity as a surki. So indeed, yes, you can actually use waste brick as surki. There's a question about what is the purpose of gypsum in cement, and of course that I'll come to in the later stages of this chapter. I'll tell you why gypsum is added, and you'll learn a lot more about that, of course, in the cement chemistry part. But for now, let me just say that gypsum is added as a set regulator. Without gypsum, your cement will not be able to react with water in the way that it normally does. See, when you test cement in the lab, you might see that the setting time of cement is anywhere between 1 to 4 hours. It takes about that long to set, and that is good because it gives you time to actually work with the cement, to place the concrete, to compact it, to finish it and all that. If your cement sets suddenly right after reaction with water, then you would have a problem, right? So gypsum is added to ensure that that does not happen. Now why it does not happen, what are the problems associated with that, we will come to that in the cement chemistry part. Why alumina, iron are considered as impurities in raw material? Actually, uh, well, I should not say these are impurities. These are impurities from the viewpoint of limestone itself. Now, limestone primarily is calcium carbonate. That's why I said iron and alumina are impurities that are present in the limestone. But then still, those are important as far as cement manufacture is concerned, because they are adding to the overall ingredients that we actually want in the cement manufacturing process. Uh, at what temperature grade of cement changes? Okay, uh, I I don't think there is any relationship between grade of cement and temperature. Uh, I'll talk about what the grade of cement is all about a little bit later when we talk about cement composition. Can any, so one more question is, can any man-made alternative material be used instead of lime? Now again, as far as sources for cement manufacture are concerned, limestone is the best possible source that you could actually use. Uh, no other man-made material would be able to give you the right blend of ingredients that you really need to actually manufacture this kind of a material. If you even look at the minerals or materials that are available on the earth's crust, which are available for mining operations, you'll see that 99, close to 99% of the elements that are present in the earth crust are basically the elements that we use in cement manufacture. We use silicon, we use calcium, aluminum, iron. So these are these are actually 98% to 99% of what you can actually find on the earth. So there is no real way to choose an alternative material that can substitute our conventionally produced cement. One question on admixture used for fire protection. Of course, this is beyond the scope of this lecture. We'll come to that probably towards the last segment. Uh, okay, what are the options other than limestone for composition of cement in such areas where it is in very less amount? Now, please remember, again, I'll come back to the same point that limestone is the best choice as far as cement manufacture is concerned. You really can't have a substitute for limestone, but in some cases, as I told you earlier, one source of calcium oxide is also marl, which is basically limestone which has a lot of clay impurities. So instead of using a pure limestone, you can actually use sources like marl, which still have a substantially large amount of calcium carbonate that can be given. Another source is dolomite, but then dolomite has a lot of magnesium in it and sometimes may not prove to be quite useful for cement manufacturing. Impurities, how do they affect the property of cement? Of course, please remember the impurities that I talked about so far are the impurities that are found in limestone deposits and in the clay, and these are actually contributing to the proportioning process of the cement manufacture. So they are not really affecting cement properties because we are only making cement now. Okay. Is there any replacement for gypsum? That's one of the questions. The problem is gypsum itself contributes sulfates, right? And these sulfates are the ones which are required for a controlled hydration to take place. Again, this is something we'll discuss in the cement chemistry chapter. Now, there are other alternative substitutes for gypsum such as phosphogypsum that comes from an industrial manufacturing process as a byproduct or a waste product. Phosphogypsum is being largely used by cement manufacturing plants instead of natural gypsum, which is not easily available. But problem is phosphogypsum always does not result in the same degree of quality control as you get with natural gypsum. So that may end up being a problem. But people are using it. They are producing cement which has required degree of control because then they need to understand how this phosphogypsum affects other properties and ensure that they have covered all the ground properly. Okay, now several questions that are related to this basically are going to come up later in the interactions that we'll have subsequently. Okay, again questions on dry process and wet process. I'll come to that in just a minute. Once we are done with this question session, we'll get back to the process of manufacturing. We look at the individual constituents of cement manufacturing, and that will hopefully answer your question easily. Okay. Again, one question is, what is the need of using wet process if we can manufacture cement by dry process with proper consistency? Again, this is a question that will be answered subsequently when we discuss. There's a question on what is the effect of sulfate on OPC. Again, we have discussed this. Basically, it's to ensure that you have a controlled setting possible. Again, we'll discuss that when we get to cement chemistry also. Green concrete, again, whether it can be used in every construction. So please remember, ultimately it's not the cement, but it's the concrete that you're going to be designing for the construction process. So if you have a good way of doing your mix design, ensuring that you are conserving your material resources properly, ensuring that you are using the right kind of cement substitutes, okay, you can produce what is known as green concrete. Okay, but please remember this, that cement manufacturing, although cement is a great material, it's a very important material as far as construction is concerned. Cement manufacturing is an energy intensive process. So lot of energy is consumed for the manufacture of cement. Secondly, cement also releases a lot of carbon dioxide into the atmosphere, the production of cement. So it is estimated that for every ton of clinker that you produce, almost 1 ton equivalent of carbon dioxide is actually released into the atmosphere. So in reality, cement production is contributing to nearly 6% of worldwide carbon dioxide emissions. So when we make concrete, we can make it more environmentally sustainable by replacing cement with other supplementary materials like fly ash or slag, because these are materials that are obtained either as waste or as byproducts from other manufacturing industries, and they can really help improve the quality of concrete without using excessive amounts of cement in the concrete. Okay. Again, I'll have more on that when we talk about blended cements a little bit later in our cement composition chapter. Okay, there's a question on what is the clay mineral. Now, of course, clays are composed of different types of minerals. One of the most common forms of clays is kaolinite. Kaolinite contributes very good source of silica and alumina. You can also have other types of clays like illite. Of course, in this case, please remember that you are only using the clay to obtain the silica and alumina out of it. So, mostly it is not really of a concern as to what type of clay or what mineral of clay you are using, as long as you get the right proportions of silica and alumina from it for the cement manufacturing process. There is a question on usable time of cement. Now this is not something that you have looked at so far in the production process, but we will talk about this when we look at the properties that are desired from cement. But in general, usable time of cement is related to how long you can actually use cement after it's been manufactured. If you keep it in very good conditions, for example, if you have very dry conditions in which you're storing your cement bags, cement probably is good enough for 3 months. But if you have a conditions where you are using cement in extremely moist circumstances, you don't have a very good storage facility for the cement, then obviously you need to cut down the amount of time that you take to use up the entire cement. Now, just like food, cement also should be used as fresh as possible. There is no way that you can store cement for very long periods of time and still expect it to perform very well. You have to ensure that as far as possible, cement is used as fresh as possible. Okay. So even in labs, when we have very highly controlled conditions, we never prescribe more than 3 months of storage of cement, because that would be really uh, amounting to bringing out changes in the cement properties with time. Okay, there's a question about Vogue compound and when we'll add water in the wet process. These are some things that we'll again discuss towards the later part of the lecture and in the next segment on cement composition also. Cement, and look at the individual processes that are involved in the cement production. Okay, we'll start with pulverization. Now, this is only common sense that when you have very coarse material, when you have large pieces, they don't seem to mix up well together. On the other hand, if you can powder the coarse materials to a very fine size, you can produce the best interaction by mixing these materials together properly. Okay, so pulverization is basically the process of grinding the material to a very fine size. So the raw material feedstock, that is your limestone and clay, has to be ground to the finest size possible. Now when you do this, it ensures that the mixing of the cement or rather mixing of the raw materials is very good. Secondly, because the kiln process involves burning of these materials together, it will also reduce the overall power consumption. So you're going to reduce the amount of power or energy required to actually produce a cement if you have burnt the material well enough. And of course, there's better blending and burning possible with reduced size of material. Just as a guideline, the desired size that you expect after grinding process is a residue of 1% on the 200 micron sieve and 12% on the 90 micron sieve. So please remember, we are grinding it already very fine. We are, even before the process of cement manufacture has started, the raw materials are being ground to a very fine size. We expect a residue of only 1% on a 200 micron sieve. We know that sand typically is of sizes between 4.75 millimeters and 150 microns, and very few particles are less than 150 microns. So we are already at a very fine sand scale when we are done with pulverizing the raw materials of cement. There are several different equipment that are used for this process. You can have jaw crushers, roll crushers, impact crushers, hammer crushers, gyratory crushers, ball mills, roller presses. You can also have classifiers that ensure that you are collecting the right kind of material after the grinding process. Whatever is oversized is sent back into the grinding process, and you end up grinding this again to get the right size out of it. Okay. So I'm not going to go into the specifics of the equipment, which is much beyond the scale of what a civil engineer can do. The purpose of this is to understand how cement manufacturing produces cement of different types and how we can actually ensure that we get the best material for concrete construction. Now, this is something that people had raised earlier about why one would choose a wet process and why one would choose a dry process. Now, of course, even before I start off, let me tell you that today, if you look at the cement plants worldwide, there are not too many plants that use wet process. Most plants around the world use the dry process of blending the raw materials. So we are talking about blending of the limestone and clay and other ingredients to ensure that they are present as a homogeneous mixture going into the cement kiln or rotary kiln. Okay. So the blending process can be wet or dry. Now just imagine when you are mixing something to make your food. If you mix two powders in the dry form, the mixing will not be as good as if you actually put both the powders in water and then you try to blend it together. Just like mixing colors during Holi, for instance, right? If you try to mix the colors dry, you will not get a very good color or resultant mixed color. If you mix it in water, you get a very good blend. Just like that, even in blending of raw materials in cement manufacture, when you do a wet blend, you get a much better consistency, you get a much better mixing of the cement raw materials. But the problem now is, now since you have added the two raw materials into water, the typical constituents are 50% water and 50% mixture of raw materials. So for every ton of the raw material feed that you are going to put into the kiln, there is 500 kilograms of water that needs to be driven off. So all this water that you are putting in the wet process to mix the slurry to make the slurry has now got to be driven off in the heating in the kiln. So you need to spend a lot more energy for every ton of clinker that you produce with the wet process, because obviously you have a lot of water which is not going to be part of the system in the end, so it has to be removed. Okay. So while the wet process gives you better mixing, the dry process gives you much higher output and lower power consumption. Okay. So just to give you numbers, the power consumption in dry process is only 3000 kilojoules per kilogram, as opposed to the wet process where it is 5500. Please remember, bulk of that energy is simply going off to drive the water away, and remaining part only is used to actually fuse the clinker and get the right compounds inside the rotary kiln. So today, dry process with preheaters and precalciners are what are typically used. There are some times when people manufacture in a semi-wet process also, especially when you extract the raw material in a slightly wet condition. Now that is the real reason why we even want to go for something like a wet manufacturing. Otherwise, it's simply not making business sense to go for a plant that has a wet manufacturing process. So just to look at some guidelines adopted by companies to go for wet or dry manufacturing, when the raw materials have a moisture content which is greater than 15 to 20%, already when you're extracting the raw material, they come very wet. In that case, maybe it's advantageous to simply grind it and blend it in a wet form, because already there's a lot of water present in it. But in most cases, when moisture content is low in the raw material deposit, like less than 8%, you do a dry blending. Okay. So in that case, all the water that is present will be naturally removed in the blending and the early clinkering process. When your water content is somewhere in between 8 to 15%, you prepare what is known as a raw meal slurry, similar to wet process, and then you send it to a very small kiln to drive off that water before the material actually goes into the rotary kiln. The idea is that the rotary kiln length should not get increased and the power consumption should not get increased because of this water that is present in the raw material. So that's why you adopt this process where you send it through a very short kiln with a cyclonic preheater. Nevertheless, wet process does give you a better blend, but today of course it's not really useful to talk about it because most plants are dry process plants. One example of a semi-wet process plant is the Associated Cement Company's plant in Madukkarai near Coimbatore, where we still have the semi-wet process adopted because of the kind of limestone that you get there. But most plants that are located in the Ariyalur belt of Tamil Nadu, and if you go to the Kadapa belt in Andhra Pradesh, most of these are actually dry process plants. okay. So once this material has been blended, in most cases we have what is known as a preheater tower, through which the blended raw material, that means the raw material clay and limestone which has been pulverized and then mixed together, it goes through this stack of towers known as a preheater tower. Now this preheater tower has several of these stacks. You see here the feed that is coming in at one end goes through several of these cyclonic stacks. Now if you look at this one example of the cyclonic stack, which is relocated here on the image on the right. So essentially what this is doing, this is the principle adopted in cyclonic separators, right. So what you do is you separate out the cleaner air and the dust by using cyclonic separators. So the same principle is adopted in a preheater tower cyclonic separator, in which you put in the feed, and what it simply does is it has a cyclonic motion with which the powder, actually the mixed powder, goes into this preheater, and the heat that is generated in the preheater is getting rid of all the moisture that is present inside the raw material. Now in this cyclonic process, when this mixture is inside the cyclonic preheater, there is also a much better mixing that is taking place, and ultimately all the material then comes out and goes into the rotary kiln, which is at the end of this preheater tower. Interestingly, most modern plants would also employ some burning inside the preheater tower itself. In other words, they call it a pre-calciner, in which process what they do is they introduce some fuel into the preheater, and this fuel actually burns part of the material even before it goes to the rotary kiln. Now what is the advantage here? One of the most important processes as far as cement manufacture is concerned is the removal of carbon dioxide from calcium carbonate, because you know that that's the requirement, because we want to get calcium oxide. So calcium carbonate, when you heat it to 7 to 900 degrees Celsius, removes carbon dioxide and you get calcium oxide. So that part is the one which actually contributes to the carbon dioxide emission also. Okay, so now you get calcium oxide at very high temperatures. Now what if these high temperatures are reached within the pre-calciner itself? That would further reduce the amount of time that the material needs to spend inside the rotary kiln, right, because part of your process is already complete. So that's why most modern cement plants tend to employ what is known as a pre-calciner, where some amount of burning actually takes place within this preheater tower itself. As a result, about 70 to 80% of your removal of carbon dioxide from the limestone gets completed in the pre-calciner itself, and then the material comes to the rotary kiln, where the other processes can now take place. Okay, so these are processes that have really improved the efficiency of cement manufacture, have reduced the overall cost that it takes to manufacture a kilogram of cement. So these are also processes that have brought in much better quality into the cement manufacturing process. Alright, now the most important part obviously in cement manufacture is the burning of the raw materials together in the kiln. Okay, now these kilns, of course I told you earlier, in the past people use the vertical or beehive type kilns, but today only rotary type kilns are actually used. Typical kilns are really long, 30 to 70 meters in size, and some of these are 5 to 6 meters in diameter. So you can imagine these are substantially large pieces of equipment. Okay, of course the length of kiln depends on the blending process. If you have a dry process, your kilns are shorter. If you have a wet process, in order to drive off the excess water that is present in the slurry, you need to make much longer kilns. Okay, so the dry process involves smaller kilns, the wet process involves longer kilns. So obviously the dry process is much lesser costly, much less expensive as opposed to the wet process. Okay, so inside the kiln, the temperature, as I told you, I showed you the kiln earlier with the source of the fuel at one end, where the fuel source is, the temperature is close to about 1500 degrees Celsius, and at the inlet point where the material is coming from the preheater, the temperature can be up to 800 to 850 degrees Celsius. So what you need to understand is the cement reactions, the reactions that form the cementitious compounds do not get completed inside the kiln itself. The process actually completes only when this material comes out of the kiln and goes through the cooling process. What comes out of the kiln after cooling is called the clinker, cement clinker, and that's what goes in the final stages of cement manufacture, where it gets ground with gypsum and other additives to make your Portland cement. Now Again, there is a lot of chemistry, there is a lot of geology that is required to really understand the reactions that take place inside the kiln, but I will run you through some of the important reactions that happen inside so that you are able to understand how these compounds actually get formed. Okay. So, the clinkering reactions primarily involve the conversion of calcium carbonate and silica and the alumina bearing components to a special mixture of different types of compounds which have the possibility to react with water and set and harden in a reasonably good amount of time. Okay. The majority of the reaction ends up producing impure but well crystallized fine crystals of tricalcium silicate, that is C3S, and dicalcium silicate, that is C2S, as we talked about previously. Okay. So, you are still producing crystalline components, but these are fine crystals of size less than 50 micrometers. Okay. But there are also other reactions that take place which lead to very interesting properties of the cement. You form the aluminate compounds C3A, that is tricalcium aluminate, and C4AF, that is calcium aluminate ferrite solid solution. But these are minor compounds that are also formed, but they are also having a very large influence on the cement behavior when cement actually reacts with water. Now, what we have to also understand is, apart from these major compounds, there are also some minor amounts of some components that are present, soluble crystalline components, primarily alkali sulfates and calcium alkali sulfates that are present. These are present usually on the surface of the grains of the clinker particles like C3S and C2S. Now, these impurities, which is alkali sulfates, interestingly give very useful properties to the behavior of your tricalcium silicate and dicalcium silicate. That is why earlier I had said that C3S is a pure form, whereas alite is an impure form of C3S. So, when the sulfates, alkalis and sulfates are present on the surface of these clinker particles, then they are called alite particles and not C3S particles. Okay. So, this is a typical schematic diagram of the cement kiln. Okay. As I told you, the material that comes in is at this end, it comes in from the preheater tower, the raw feed actually comes in here. Okay. In the earliest stages, you have the dehydration zone, that means the free water that is present in the system gets removed. Obviously, water gets removed at temperatures of around 100 degrees Celsius. So, all the free water gets removed very early in the process. Somewhat later, probably closer to about 600 degrees Celsius. Please look at this chart carefully. There are two temperatures given here. One is the gas temperature, okay, and one is the feed temperature. So, gas temperature is what is generated by burning of the fuel inside the kiln, okay, but not all of that heat is directly taken up by the raw material that is coming in. So, that feed temperature is typically lower than the gas temperature close to the inlet. Okay. So, here the free water is first going out. At around 600 degrees to 700 degrees, the clay starts decomposing. So, what do I mean by decomposition of clay? Please remember, the clay is an aluminosilicate which has a layered structure, right. These layers are sometimes bound together by ions, sometimes by water. When you reach temperatures of around 6 to 700 degrees Celsius, these layers of clay are activated. Okay. So, the layers get free and start becoming reactive around 6 to 700 degrees Celsius. Soon after that, you have a temperature where your limestone is decomposing. Now, please remember that this is a process in the absence of a preheater or precalciner. In the presence of a preheater of precalciner, much of this, that is removal of free water, the decomposition of clay, some part of decarbonation of limestone, all that would have taken place already in the precalciner, and the material that comes into the kiln will directly be able to start its reaction. Okay. So, what I am trying to show here is that this clay is decomposing and giving you SiO2 and Al2O3. The limestone is decomposing and giving you CaO, calcium oxide. Okay. So, formation of the initial compounds starts happening soon after the limestone decomposes. So, around at a temperature of 900 degrees Celsius, you have the formation of the initial compounds, basically calcium silicate in the form of C2S, dicalcium silicate. So, initial formation of C2S happens in this case. Now, when you reach a temperature of about 1350 degrees Celsius, there is a molten phase that appears in the process. This molten phase is actually a combination of the calcium aluminate and calcium aluminate ferrite solid solution. So, this molten phase appearance is of great importance because this now promotes the transformation of C2S to C3S. Now, if you take any modern cement, it is mainly composed of C3S. Now, why is it mainly composed of C3S? Because we want the cement to attain strength very early, because most modern construction projects we want the concrete to gain strength very fast, and the ingredient in cement that contributes to early strength gain is C3S. Okay. So, this last stage of cement manufacture is very important, or the kiln reactions is very important. Here is when the C2S with additional lime, that is calcium oxide, gets transformed into C3S, and the reason that this reaction is promoted is because of the formation of this molten phase that has appeared at around 1350 degrees Celsius. Okay. So, finally, when the kiln process is over, you get a mixture of C3S, C2S and the molten phases, and this now has to go out of the kiln and go to the cooling chamber or cooling grate. Okay. So, it goes to the cooling process after it comes out of the kiln. So, just to put this in perspective again, I have presented here one more picture of what reactions actually take place inside the kiln. Okay. So, up to 700 degrees Celsius you have the activation of silicates. So, basically silica and alumina become available in the system for reaction. 7 to 900 degrees Celsius, decarbonation of calcium carbonate, that means removal of carbon dioxide and freeing up of calcium oxide. Then you start combining calcium oxide with the silica, alumina and iron. 900 to 1200, the formation of C2S takes place. Greater than 1250 and close to 1300 degrees Celsius, you have the molten phase appearance, which promotes the formation of C3S from C2S, and then in the cooling stage you finally get your actual cement. Now, the cooling stage is also very interesting, because if you cool at very slow rate, if you take the clinker that comes out and cool it very slowly, you may have the problem of crystallizing the aluminate, which will lead to setting problems in your cement. Cement won't set properly at all. And if you cool it very slowly, there is also the danger that you convert your C3S, tricalcium silicate, back to C2S. Now, why is that a problem? First of all, we have made our cement with higher C3S content to ensure we get very high early strength. If you have more C2S and less C3S, you will get lower early strength. Secondly, when C3S converts back to C2S, it also releases calcium oxide, that is free lime, and free lime in the system contributes to what we call as unsoundness. Okay, one of the tests that you would have done in the lab with cement is the soundness test. So, when cement reacts with water, if it is unsound, it will lead to expansion, and that happens because of the free calcium oxide that is present in the system. Okay, so cooling has to be done in two stages. Typically, up to 1200 degrees Celsius, the clinker is cooled suddenly, and after 1200 degrees Celsius, because what happens is at 1200 you are now back to this temperature, so there is no danger of conversion of C3S back to C2S, and the molten phase also would have become solid at the conversion of the after the 1200 degrees Celsius temperature. After 1200 degrees Celsius, the clinker is cooled at a slow rate to the normal ambient atmospheric temperature. Okay. So, that is a snapshot of a clinker cooler. If you can see the image on the left actually shows you the molten phase that is coming out of the cement kiln, and it is actually going through this grate cooler, and then it is cooling down to form the right nodules of the cement. So, this is another type of cooler. Manufacturing equipment actually taken, the picture has been taken at the manufacturing facility of the cooling equipment. So, that is the typical layout of your cooler. Okay, so clinker has now come out. So, the clinker I showed you earlier in the cement plant pictures, that clinker has come out in the form of nodules, and now this has to be ground to the right size to make cement. At the time of grinding, as I told you earlier, we add the other additives in the process. So, you have your gypsum, which is added as a set regulator. Okay. In the absence of gypsum, we have a condition called flash setting. So, if you do not add gypsum to your cement, it reacts very fast with water, liberates lot of heat, and sets immediately, and you can't simply use that cement or concrete anymore. That's called flash setting. Now you don't want that. To ensure that you don't get flash setting, you need to add gypsum in the process. So in this final stage of cement manufacture, you add gypsum to the clinker and then grind it together in a ball mill. As I told you earlier, the ball mill is a rotating drum where you put steel balls which are colliding with each other and grinding the clinker and gypsum together on impact. Other additives that you may have in the system like fly ash or limestone, those may also be added during this stage. Okay, this is the final stage where you can add any sort of additives. You might have heard of blended cements like Portland porcelain cement or Portland slag cement. The fly ash or slag that are used to make those blended cements are added during this process of the final grinding. Okay, and ball mills are today being replaced by more efficient roller presses. So you have two rollers, basically the raw material comes in, the two rollers are pressing the raw material together, and that's a much more higher energy efficient grinding process that leads to the formation of very good fine sized cement particles without too much energy being spent in the process. So there are several changes to manufacturing technology that have taken place, but ultimately this is ending up producing cement of the required fineness. So that's the importance of the intergrinding process with gypsum. Now one thing you may have to understand, which will be of importance later when we talk about cement chemistry, is that while intergrinding the gypsum with the cement, you need to have a strict control on the temperature. Now why is this done? Because you know very well that gypsum is calcium sulfate with two molecules of water. So I'll just explain this on the board just for some clarity. So gypsum is calcium sulfate okay. So when you add gypsum to the clinker and mix it or grind it in the ball mill, if your temperature goes to between 100 to 120 Celsius, what may end up happening, you might have seen this before, you must have worked with plaster of Paris obviously. So when you heat this gypsum up to 100 to 120 degrees Celsius, this converts to plaster of Paris, that is CaSO4 half H2O. If heating is still further at a higher temperature, maybe around 130, 140 degrees Celsius, this may convert again to calcium sulfate without any water, or we call it anhydrite. Okay, that's anhydrite, and that is hemihydrate. Now why is this important? What is the problem with this entire thing? The problem is this sulfate has to be available in the cement to react, okay, and sulfate is coming from the solubility of the gypsum. So gypsum has to dissolve and release the sulfate. The sulfate comes into the reaction and reacts with the aluminates to form different compounds, which we'll talk about in cement chemistry, but the rate of solubility of these compounds could be quite different. For example, if you take gypsum and heat it to a hemihydrate, its solubility actually increases. That means you get more sulfate very quickly into the solution. If you heat hemihydrate to anhydrite, the solubility still further increases. Okay, so from natural gypsum, when you heat it, you get hemihydrate, heat it further, you get anhydrite, the solubility is quite different. As a result, if you don't know what blend you have in your cement in terms of what type of sulfate you have, then you don't have a means of predicting how the initial setting and hardening behavior is going to be. So it's very important for us to have a very clear cut temperature control in the process, so that we have a right idea about what type of sulfate is actually ending up in the cement. Okay, I'll come back to this when we talk about cement chemistry in the last part of this module, but we'll come back now to the cement grinding and manufacturing process. Now earlier during the interactions with the different participants, I had mentioned that one of the common forms of gypsum that people are using nowadays is phosphogypsum, which actually is a waste or byproduct from the fertilizer industry. Okay, this is of course cement companies want to cut down their production costs, and one way to do that is to find substitutes for naturally occurring materials which are not always in abundance. For example, I have seen cement plants that actually import their gypsum from countries in the Middle East to ensure that they have the right quality material to do their cement production process. Now phosphogypsum comes from the fertilizer industry and it presents a very viable alternative to the use of natural gypsum in the process of cement manufacture. However, it may not behave exactly the same as regular gypsum. Okay, so this is an important stage in cement manufacturing because you're producing cement of the right fineness. At the same time, you're also having different blending or different types of gypsum in your process, like anhydrite or hemihydrate or dihydrate, which is regular gypsum, which may affect the kind of reaction that you ultimately get when cement reacts with water. Okay, we'll come back to that with more clarity in cement chemistry. So right now let's just continue here, just a couple of more slides to go and then we'll be done with the production set in this module and then I'll again open the floor for questions. Okay, now of course because of the issues involved in this cement manufacturing process, you can imagine that you are extracting naturally occurring material, you are subjecting it to a very large set of processes and ultimately you want to end up with a material that is highly well controlled in terms of physical properties and chemical composition. So to do this, there is got to be a very high degree of quality control that needs to be adopted in this process. You might have seen that when you buy different brands of cement from the market, although all of them claim to be 50 grade cement, the kind of concrete that you end up producing with these cements is quite different. Sometimes you don't get the right strengths with the 50 grade cement or a 40 grade cement and so on. Okay, you might have seen several times in your research projects in your institutes that when you change the brand of cement, suddenly your overall system itself changes. You are not able to get the same results that you got with the older cement. And in production, in the concrete construction process, this is all the more important because the construction process takes place over a period of several months or probably several years. During this process, they'll have to probably go through several different batches of cement, several types, several brands, and several batches of the same brand of cement. So if there is variability, there's got to be a major issue with the quality control in the system. So to avoid variability in the cement, in the kind of cement that is being produced, cement companies spend a lot of time doing quality control, and this quality control during cement manufacture is done at every stage in the process. Now, what do I mean by every stage? I literally mean every stage because sampling and evaluation of the material is done in several stages. One, you have after excavation from the quarry because you want to know if you have the right kind of material that has been removed, before and after blending the raw materials together because the right composition has to also end up in the final blend that you select, after formation of the clinker, right, because ultimately that is what is coming out of the kiln and you need to evaluate that with respect to its oxide and compound constituents, and after intergrinding the clinker with the gypsum, and finally before packaging in bags and drums, because ultimately you don't want at any stage the composition to go out of a given strict range because you want the cement to have a very clear cut predictable performance in the concrete, and this has to happen between several batches that you produce in the same day, several batches that you produce across a given month, right. And this is why it's very important to understand that you have to use cement in as fresh a state as possible because oftentimes the variability between the batches which are produced in different months may be quite different. So once you have a stock of cement, you have to use it up as early as possible. So what are the parameters that have to be looked at as far as quality control is concerned? Okay, one very important parameter is what is called as lime saturation factor, LSF. Okay, lime saturation factor. The equation for that is given on the top here. Lime saturation factor is usually expressed as a percentage. So this is only giving a ratio, but usually it's expressed as a percentage. So as a percentage, it's the amount of calcium oxide. Please remember, C is calcium oxide, S is silicon dioxide, SiO2, A is aluminum oxide, and F is iron oxide. So let me just write this again on the board for clarity. C is calcium oxide, S is silicon dioxide, A is aluminum oxide, and F is iron oxide. Okay. So here the lime saturation factor is basically giving you an equation where it relates to the amount of calcium oxide to some weighted fraction of the amounts of alumina iron and silica. So C divided by 2.8 S plus 1.2 A plus 0.65 F. Now you may be wondering why this sort of a complicated equation. Now this is some sort of a way to adjust the quantities in such a way that you are getting the right blend of your C3S, C2S, C3A and C4AF. In other words, this lime saturation factor is actually telling you how well combined your calcium is with the silica, alumina and iron oxide, because I told you earlier that we want a mixture of C3S, that is tricalcium silicate, C2S dicalcium silicate, C3A tricalcium aluminate and C4AF, that is calcium aluminate ferrite. Okay, so this equation basically tells you how well the calcium is actually combined. As a result, because earlier I told you if you have free lime in the system, that is free calcium oxide, it leads to unsoundness. So you need to ensure that this lime saturation factor should be kept generally between 92 and 98%. Okay, this ratio of C divided by 2.8 S plus 1.2 A plus 0.65 F, this ratio should be kept between 92 to 98% to get the best results as far as cement is concerned. If you have more than 100%, this indicates the presence of free lime in the system, which is going to be a disadvantage for the cement. It is going to cause unsoundness in the cement. Okay. Then the other parameter to look at is the silica ratio or silica modulus, which is the ratio of the silica content SiO2 to the sum total of the alumina and iron oxide content, S divided by A plus F. Generally, this is between 2 to 3. Okay, this is not as a percentage, I am just presenting a ratio. So this is between 2 and 3. Alumina ratio or alumina modulus is equal to alumina content divided by iron oxide content. This is typically 1 to 4. Again, it's a ratio, not as a percentage, it's a ratio between 1 to 4. And then you also get the potential tricalcium silicate content from Vogue formulation. I told you earlier that modern cements are based on producing very high quantities of C3S because that leads to the highest rate of strength gain for your concrete. Okay, so we are interested in seeing whether the cement that we are producing is producing the right quantity of C3S. What is Vogue formulation? We'll come to that in the next chapter on cement composition, but for now this is one of the parameters that needs to be checked by quality control. So again, lime saturation factor, I told you already, it's particularly important because it dictates how much lime or free lime is present in the system. If you have too much free lime, it leads to unsoundness of the cement. Okay, so with that we've come to the end of this segment on cement production. I know there must be several questions in your mind, but I also wanted to point out one website that I have which may be of a lot of use to all of you. I'll just write the website address on the board so that you can refer to the notes on the website also, because most of these materials you must have got as handouts, but you can also refer to that on the website. So it's www.theconcreteportal.com. So this website is free to use. You can easily access all the material that is there in this website. Much of the content that I am covering in these modules will also be available on the website, so you can actually refer to it anytime. Most of you have smartphones, you can get it on your mobile if you have a 3G connection, and you can actually refer to these. Please remember, this is only a summary of the notes that I have used for my class lectures and everything. It is also presenting content that is presented in several different textbooks, but I still prescribe that all of you who are interested in concrete technology, particularly in cement, to purchase one or more of the textbooks that are available. I'll give you at least 2 authors whose textbooks you can buy to get a lot of good information on concrete. So some good textbooks. One, you have, the author's name is A.M. Neville. Okay. Second is Mehta and Montero. Okay, these 2 textbooks on cement chemistry and concrete technology are really useful. They present a lot of information, a lot of interesting research based information is also analyzed critically in these textbooks, and the information has been presented in a way that people can understand very easily. okay. And I really prescribe those of you interested in concrete technology to purchase one of these. Both of them are available in Indian editions for fairly inexpensive rates, and most of the bookshops also carry these books. So please do get yourself a copy of these books. The website is only intended to give you a snapshot of what information can be overall covered in this subject, but it is not intended to be a substitute for good quality textbook. So one of these two textbooks is a must for any person who is interested in concrete technology, okay. Uh, well, so I'll again open the floor for questions. So we still have a few minutes left in this session. So it'll be good if you can raise your questions, mostly related to the content that we have covered. If you have other questions also, I have no problem answering them. But as far as cement composition and chemistry are concerned, most of those questions will be answered anyway in the sessions to follow. So anyway, right now we'll open the floor for questions and interactions, if any. Okay, there are already some questions that were posted. One question is it possible to use hemoglobin as one of the binding materials? That's an interesting question. I don't know where the source of the hemoglobin can be from other than from blood, but I don't want to be putting blood in cement manufacturing process. Uh, uh, so I don't know if that's a very good way to use iron in the process. Okay. Is it possible to use lime sludge from leather industries in the clinker process or in cement production? Now again, you have to evaluate the lime sludge very carefully, see the content of lime that it's giving, and also ensure that the kind of impurities that you may have in the system are restricted to the right level possible. Please remember, once again, I've told you this before, that cement production has to be a very highly controlled process, resulting in the formation of a compound that is within a given range of chemical composition. It needs to perform perfectly all the time, as a result of which when you start putting impurities in it, you need to be very clear about what are the contents that it's actually bringing to the system. So lime sludge, people have shown the use of lime sludge in concrete, but not in the process of manufacturing of the cement, but it may be an interesting contributor to the cement also, provided we have a way of removing the impurities, because we don't want to put impurities in the system. What are the reactions that take place when cement is stored in wet climate for a long time? Again, this is cement hydration that takes place. Cement reacts with water. So if you have moisture in the atmosphere, your cement is going to start reacting, as a result of which the bags which have been stored in wet conditions for a long time, you may see they've already started becoming hard. If you start pounding on the top of the bag, you'll find a lot of lumps inside. So that means cement has actually already started reacting, although on the surface, not totally inside, but still it has started reacting. That means it has become poorer, its quality is reduced. Okay, so that's why generally, if you are storing in very good dry conditions, you can use cement up to 6. But if you're storing in wet conditions, then it's simply not good to actually use the cement for a for even more than a 2-week duration. Okay. Uh, Now, of course, one question that has been asked is effect of type of sulfates such as hemihydrate or anhydrite on cement chemistry. Once again, without getting into the details, which I'll be covering a little later in cement chemistry, let me just tell you that the use of gypsum in different forms affects the rate at which the sulfate is available for reaction. Okay, and availability of sulfate is a very important consideration as far as the speed of the reaction is concerned. Okay, and I'll leave it that when you actually come to the reactions in cement chemistry, you'll understand that much better yourself. What is the effect of adding gypsum on water to cement ratio? Again, please remember, we are not interested in gypsum itself. Okay, we are only interested in the cement. So you are designing concrete with the cement. So you don't know, as a civil engineer, you don't really have a choice of what's inside the cement. It's only the cement manufacturers who can make a difference by putting different type of ingredients in the cement. Ultimately, as long as the cement is passing all your quality control tests, which you typically do in your lab, like fineness, setting time, consistency, all those kinds of things, as long as that is satisfied, your cement is suitable for use in the construction project. So you don't really have to worry about why gypsum would be affecting water cement ratio. It does not affect water cement ratio, but it affects the rate at which water is consumed in the reaction, that we will see in cement chemistry. What is the quality difference between dry process and wet process? Okay, now again, as I told you, when you are trying to mix powders in a wet condition, their intermixing is going to be much better as opposed to the dry condition. But since the dry condition also involves the preheater tower, where I told you already that the cyclonic sort of a action takes place, the cyclonic action ensures that even in a dry process you get a very good blend. So as long as your raw material blending is good, the kind of cement that you produce will not be different as far as dry or wet process is concerned. But only you have to remember that when you have a wet process, there is a lot of water to be driven off, and this water is driven off during the kiln reaction, okay, when the clinkering process happens in the kiln. So you need to spend a lot more energy and you get lesser output in the wet process. But otherwise the quality difference, you can avoid that by a proper quality control in your process. And what is unsoundness and how does it affect strength? Okay, please remember unsoundness is related to the expansion that happens to the cement when it reacts with water. Now in normal situation, we don't want the cement to expand on hardening. If it expands on hardening, then you will have unnecessary cracking in the system. Okay, you don't want unnecessary cracking. Because of that, you want sound cement. That means cement that does not expand on hydration. And the free lime or free magnesium oxide sometimes can lead to unsoundness, and those need to be controlled to a large extent. Okay, one question on what is feed temperature. So as I told you earlier, the raw feed is coming inside the rotary kiln and moving by gravity to the other end, and the fuel source is located at the other end of the rotary kiln. So the temperature here is the highest at the fuel source, and at the end of the raw feed coming in, the temperature is at its lowest. Okay, so now the fuel is getting burnt, and the gas that is present that is generated by the burning, that has a temperature which is heating up the raw feed which is coming in at one end. Okay, so the temperature of the feed reflects the temperature of the raw material inside the kiln, whereas the temperature of the gas could be quite different, could be quite much a lot higher than the actual temperature of the raw material itself. So feed temperature is the temperature of the raw materials inside the kiln. Lime is present in Surki. Why leakage occurs? I am not very sure. I'm not sure why leakage is being talked about here. I'm not sure about the context of this question. If you can expand that better, I'll be able to answer that. There's a question about what is Bogue's compound. Again, Bogue compound, your C3S, C2S, C3A and C4AF. Those are the four compounds in cement. Why are they called Bogue's compounds? Because Bogue was one of the scientists who gave the equations that predicted the amount of these compounds forming from a mixture of calcium oxide, silicon dioxide, aluminum oxide and iron oxide. I'll come to these equations in the next chapter on cement composition. That's when we meet the next time. Okay. Of course, some questions are not really in the context of what we have discussed today, something on green concrete again, and another on why we can't use large stones in concrete instead of normal chips. Again, that depends on the kind of project you have. Ultimately in concrete you have to use the aggregate size based upon what is feasible, right. Generally speaking, you should be able to use the largest size aggregate in concrete, but then the aggregate size is obviously determined by the amount of reinforcement, the amount of spacing you have between the reinforcement bars, right. If you use too large an aggregate size, you can't really fill up your formwork properly and your concrete will get blocked because of the reinforcement. So your choice of aggregate size depends on the spacing available between reinforcing bars. What is the alternative to gypsum to control initial setting time? Now again, so gypsum or sulfate essentially is essential in the reaction because that reacts with the aluminates to lead to a controlled setting process. Okay, so you need sulfate in some form or the other. So that is, so any source that provides sulfates at the right level of solubility will be a good alternative to gypsum. So far people have not seen very many other compounds that reflect the same kind of solubility and the same kind of reactivity with the aluminates that are present in the cement. So right now there are no other alternatives, or at least I don't know of any other alternatives that are good enough. Which part of manufacturing process affects maximum to environment and latest advancements to decrease it? Now of course you know that there are several different processes that can contribute to environmental damage. One obviously is the removal of carbon dioxide which has to happen because carbon dioxide is getting contributed from the limestone, that is calcium carbonate. When you heat it to 700 degrees Celsius, the carbon dioxide goes out. Also, please remember you are using fuel, and when you burn the fuel, there is more carbon dioxide that is going to go out. If you have coal, for instance, right, different forms of coal, if you are burning coal, obviously that is also going to release carbon dioxide. Okay. So, all this carbon dioxide adds up to the burden on the environment. One way to reduce that, okay, you really can't change the cement manufacturing process, but you can use cleaner fuels that release lesser carbon dioxide. But as far as the calcium carbonate is concerned, there is no other substitute for that process. So, that level of carbon dioxide will anyway go out into the atmosphere. To reduce the impact of the cement production, what you can do is when you make concrete, make it with a cement replacement material like fly ash or slag. That means effectively for every ton of concrete that you produce, the impact on the environment can be reduced substantially. And truly speaking, if you go into details of the numbers, concrete is a much more carbon dioxide free or low carbon dioxide material as opposed to something like steel, which involves a lot more carbon dioxide during the manufacturing and usage process. Other environmental issues are the release of nitrogen and sulfur based oxides into the atmosphere. Now that has to be controlled to a large extent. Again, that can be done by using cleaner fuels. So there are a lot of research studies going on about different types of fuels to be used in cement manufacture, because not only are you interested in saving the environment, you are also interested in reducing the overall cost of the production process. So the effort to churn out new types of fuels which are energy efficient, which produce less environmental damage, that's all the time ongoing. What are the effect of atmospheric conditions in cement manufacture process? At what rates temperature should rise? Again, atmospheric conditions are not all that important, because outside atmosphere we are not really worried about. It's the conditions that are generated in the kiln, and that can be controlled to a large extent by the use of the right kind of fuel and the right temperature of burning. If definite proportion of alumina oxide is different, what all changes with, again please remember this, that cement manufacturing process does the quality control at several stages. So when you extract the raw material from the quarry itself and you decide on the kind of blend that you're going to be doing between limestone and clay, you're already ensuring that you are getting aluminum oxide in the right quantity. If you don't have it, then you'll be using aluminum oxide ore or bauxite as an impurity that will contribute to aluminum oxide content in the cement. So while doing the proportioning itself, you'll ensure that you have right quantities of all the oxides. Okay, so you're not going to be producing cement which has an unknown quantity of this material, because you have done this calculation prior to your production process. Another question on again size of the aggregate, but please remember we are not talking really about concrete here, but anyway the size of the aggregate is again related to what concrete you're going to be using and what is the spacing available between reinforcement. Okay, for example, if my spacing between reinforcement is 40 millimeters, then there is no point in my attempting to restrict my aggregate size to 12 millimeters. I can as well use something greater than 20 also, right, because I have sufficient space to flow the concrete between the reinforcement. Okay, so again, and also it depends on the cover to the concrete. If the cover to the concrete is only 15, then obviously I can't use aggregate of 20-25 millimeters there. Okay, that's mostly given by the choice of the engineering construction process, which involves the spacing between reinforcement. So the cement or cement type does not really have an effect on what size of the aggregate that you need to choose for the process. That's entirely based on your project at hand. What is the significance of sulfur? Again, sulfur or sulfate is required to react in a controlled manner with the aluminates to give the right degree of setting and hardening to the concrete. One question on what is geocement? No need of adding water. Now again, when you're talking about waterless cement, that has to be some sort of a polymerization process, but you still have to add an ingredient in the polymer, which typical most of these polymeric cements are of two forms, two component forms. One is an inorganic component, a filler component, the other is a polymer component. So polymer component still has to be in a form that is liquid enough to flow and then harden in a normal scale. So you really, typically speaking, you are not forming concrete without adding water at all. It's not possible to make concrete without adding water. But if you are moving to a polymeric form of cement, like a polymer cement, I'm not talking about geopolymer here, okay, that's different. I'm talking about polymer cement where there are two ingredients, one is a filler based ingredient, the other is the polymer resin, which basically is fluid in the beginning but then it slowly hardens and becomes solid. That's totally different as compared to a regular cement process. So you can't do waterless concrete production with using typical cement or cement replacement materials. You have to have water in the system. Any importance of magnesia added in the cement? So please remember, magnesia is only coming from the impure forms of limestone. So like dolomite, dolomite is calcium magnesium carbonate. So if you have a source of dolomite, that's contributing magnesia or magnesium oxide to the cement manufacturing. Now magnesium oxide is also one compound that will lead to unsoundness. So you have to control the quantity of oxide that you have in the cement, okay. So typically this is restricted to 4%. If you have more than 4% magnesium oxide, your cement is not going to be good for use. That is why the amount of dolomitic limestone that can be utilized for production is very small, and cement companies typically don't want to use dolomitic limestone because they get a lot of magnesium oxide in the process. So you don't add magnesia to the cement, it happens to be there because of the impure forms of limestone. What is the benefit of finding of silica ratio and alumina ratio? Again, it's not the purpose of benefit that the cement is getting, you only have to ensure that your manufacturing is being done with the right proportion of the ingredients. So the idea of finding silica ratio and alumina ratio is to ensure that you are always keeping your cement proportion in the right range that you want. Only by doing that you will get the correct mixture of compounds like C3S, C2S, C3A and C4A. Three grades of PPC. Again, please remember, PPC or Portland Pozzolan cement does not have any grade, okay. It's only OPC or ordinary Portland cement that has three grades, 33, 43 and 53. Again, we'll talk about this grades of cement in the next chapter on cement composition. Dry or wet process, I believe I've answered that question. Ultimately, the process depends only on the state in which the raw materials are found. If you have very wet raw materials, then you might as well go for a wet process. But generally nowadays only dry process plants are preferred because they are much more energy effective and produce a larger output for a given quantity of material that goes into the cement kiln. Uh, how does physical properties, setting time and strength change by adding fly ash and lysis cash? Again, we will talk about this later when we talk about blended cements in the cement composition section. Again, it is not truly related to what we are talking about here. What material used for invention of what material was used for construction before cement? Of course, we have talked about that, mainly lime and lime based additives which were used. How can we maintain the lime saturation factor, silica ratio, alumina ratio when we add more additives to the cement? Please remember, the lime saturation factor, silica and alumina ratio are determined for the clinker, okay. When you put the additives, it becomes cement. Now for the cement, we are not worried about those ratios. We only talk about those ratios in terms of the clinker. Now when you look at the cement standards, okay, there is 5% of additive that is permitted. When you have the 5% additive that is permitted, when you have, for example, silica that comes in by the additive, you are bound to have a change in your composition, okay, because silica, if you have fly ash for instance, you will be contributing silica to the cement. If you have limestone, you will be contributing more calcium oxide to the cement, okay. So again, the lime saturation factor for the cement will be quite different. So here we are talking about the clinker, which needs to be controlled very carefully with respect to the lime saturation factor. Okay, do you think India will become more polluted in 2050? Maybe I am not the right person to answer that question, but I know that any increased production process, higher utilization of materials, higher utilization of natural resources that we are actually seeing in our country definitely will lead to a greater amount of pollution of the land, of water, of air, everything. And one way to avoid doing that is to ensure that we are to the maximum using as much byproducts and waste that we can in the construction process and minimize the use of natural resources to the extent possible. So one way to go in that direction would be the use of recycled concrete as aggregate for new concrete, and that's something which people have already looked at, and it's presenting a lot of useful information to concrete technologists. Okay, lesser heating of or cooling during production process, what is its consequence on the quality of the product? Again, please remember all these processes are controlled properly. You have a very clear cut understanding of what level of heating is required to initiate the reactions between different components, produce the right kind of compounds and all that. So it really is not an important thing to worry about, because all this process is taken care of in the system itself. Again, controlling pollution released from cement industry is probably, that's not something within my purview, but there are several ways in which this can be done. There are several gas traps, there are several fine dust traps that can be put in the cement process, and most cement companies have to actually put these in place, because as I said earlier, the environmental regulations are quite strict on cement manufacturers today. What is blending process and what basis length of kiln is adopted? Again, blending process means mixing of the raw materials, limestone and clay. Okay, so we do it either by dry or wet process, and the length of the kiln depends on whether you have a dry or wet process. If you have a wet process, that means you need to release the excess moisture that has been used to prepare the slurry. Okay, so you have a longer kiln in a wet process. In a dry process, you'll have a shorter kiln. Can some person had asked difference between white cement and normal cement, and another person has asked, can we manufacture colored cement? Okay, one of the important aspects to understand here is that the color is contributed by the oxides, okay, and the way that these oxides are actually burning. In white cement, we choose composition in such a way that there is very little of iron oxide present in the proportions. If you have lower iron oxide content, your cement comes out to be white. If you have more iron oxide, it comes out to be grey or dark. Okay, there are other minor impurities also that are present in the cement which may contribute to color, like titanium, manganese and all that. Now generally, if you look at the perception of people, both in the industry as well as common clients, if you give them cement which is anything other than grey in color, it will not be very highly acceptable in the market. Okay, because I have seen several cements which are lighter in color, not very readily accepted by the users. So although there is technology to produce colored cement, nobody wants to do that because cement is expected to be of a certain color, and if you are deviating from that color, the acceptability or market potential of that material becomes lower and lower. Why is gypsum added only at the end but not in the blending process? Please remember, again, we want the gypsum in its calcium sulfate form. So when you add it in the blending process before the kiln burning happens, then you are going to totally convert this into a different form. You are going to drive off the sulfur trioxide as a gas, which you do not want. You want the calcium sulfate to be present in the cement. That is why it is added only during the intergrinding in the end, not before the kiln process happens. Okay, so that is why we add it only at the end. Is there any in situ test to determine the strength of cement for different brands? No, there is no in situ test. You have to do the test as per the Indian standard prescription, where the cement is mixed with sand and water, which is determined by the normal consistency of the cement, and then you prepare cubes and these cubes are to be tested. That is the only way you can actually test the cement. Classifiers are water classifiers is another question. Classifiers are systems which are used to, typically they are used to actually do cleaning of the air. That means they remove the dust from the air and leave out the clean air. But they have the cyclonic action which is actually made use of in a preheater tower. So, but classifiers are also used in cement manufacturing systems to ensure that you get the right kind of size after the raw material has been pulverized. You need the right kind of size of the raw material, and you do not want the coarser size particles. So you take the finer size particles, and coarser size particles are fed back into the grinding process. So classifiers help you classify the finer size from the coarser size. Okay, I think there are some interactions also that people want. We will go to those, and I hope I have answered most of the questions that you have. In any case, you can also, we will start the next session next week with a question and answer session also. If you have more questions about this production process, you can ask then. There are some interactions which we will go to.
It's 33.
Yes, VIT.
34. Yes,
Do you have any questions for interaction? Yeah.
Yes, sir. So what is the difference between feed temperature and gas temperature? And what is the significance of using the two different temperatures?
No, there is no specific significance. So here we are talking about the gas temperature as the burning temperature of the fuel. Okay, so fuel is actually burning and creating a temperature difference at one end of the kiln to the other. This heat that the fuel is generating is being transferred to the raw materials that are actually coming in. Okay, so the raw materials are coming in at a certain temperature, and the fuel burning transfers the heat to the raw material and changes the temperature of the raw material. So the feed temperature is the raw material temperature. The gas temperature is because of the burning of the fuel. Okay, so the feed temperature is what we need to be concerned about as far as the reactions in the system are concerned. The gas temperature is not really of a concern for us. Gas temperature, we need to ensure that it has sufficient heat to transfer it to the raw materials that are inside. Okay, BEC, do you have any questions?
Sir, can we improve the quality of the cement after manufacturing?
Okay, now see again, please remember that you are getting cement of a certain quality after manufacturing. Okay, you are not going to be changing cement quality after that. You can certainly ensure that you understand by testing what that cement is capable of doing in your concrete, and ensure that you choose your concrete mix design and proportions properly to ensure that you get a good concrete between cement and concrete. Cement is what is produced in the factory and is getting used inside a concrete mixture. You have all the necessary ingredients to help you improve the quality of concrete mixture, but you don't have a say in going back and improving the cement after it's already been manufactured. Okay, so you can always improve concrete but not necessarily the cement. Cement is the responsibility of the cement manufacturer. Okay, I think I'll just round up today's discussion with answering a few of the remaining questions. uh, One question is final setting time of cement after which concretes becomes useless. I'm not very sure what you're trying to say here. Truly speaking, after final setting time, the concrete has actually attained a given form, right? So you can't change that form after that final setting time has been achieved. So I don't think it's right to say concrete is becoming useless after that point. Really speaking, the concrete is actually becoming useful only after that point, because it is hardening and gaining strength and providing strength to your structure only after the final set. Okay. Uh, Main benefits of using dry process over wet process. Again, main benefit is that you are consuming lesser energy for manufacture of cement. Second, for every ton of raw material that you are feeding in, you are getting a larger output of cement clinker as opposed to wet process, because in the wet process you are feeding in raw material which has a lot of water, and lot of this water is getting driven out. So for every ton of raw material you're feeding it, you're getting only half ton of clinker for wet process. But in dry process, you're getting a substantially larger amount as compared to that. Heat of hydration, again this is a question that we'll attempt to understand in cement chemistry, but heat of hydration essentially means the amount of heat that is liberated when cement reacts with water. Again, there are various factors that control this, we'll talk about this in cement chemistry. Okay, what are the solid solution constituents? Again, solid solution is something which we'll talk about when we discuss the composition of cement. This relates to the calcium aluminate ferrites that are present in the system. They are not present as a single sort of a compound, but a mixture of several different compounds. That's why it's called a solid solution. Okay. Again, it's not really of any major interest to a civil engineer to really go into an understanding of what are the different types of constituents present in the solid solution, but the average formula for the solid solution is C4AF. Okay. Again, there's a question related to how much fly ash can be added to cement. Again, we'll tackle that in Portland porcelain cement understanding when we talk about cement composition. Which ingredient in cement is responsible for efflorescence in concrete and how to control it? Now again, please remember cement is not as such, it reacts with water to produce the hydrated cement paste. And one of the ingredients inside hydrated cement after it reacts with water is calcium hydroxide. Now when calcium hydroxide leaches out because of the action of water and converts to calcium carbonate on atmospheric exposure, that leads to efflorescence. Okay. So cement does not have any ingredients that create efflorescence. It is just because of leaching out of calcium hydroxide which can happen in different circumstances that you can get efflorescence, but cement itself does not have ingredients that will cause efflorescence. For example, it does not have salts in it that will precipitate out and cause efflorescence, but leaching out of calcium hydroxide under certain conditions, under action of water moving through the concrete, that may lead to efflorescence, but nothing otherwise. Okay, I think one person has raised the question which I wanted to ask in the beginning, why is cement packed in standard size like 50 kg bags? Okay, now several people have different answers for it. Some people say that it's easy to lift 50 kilograms, but those of you who have tried lifting 50 kilograms, it's not possible for one person to lift it or even two people to lift it easily. The reason why it's in 50 kilogram is because of the old days people used to do construction in volumetric proportions. Like if you go to smaller residential sites where people are doing mixing of concrete by hand, by putting ingredients down on the road and then mixing it together, you might see that they have this bucket which actually is a cubical bucket which approximately measures 1 cubic foot, 1 foot by 1 foot by 1 foot, that is the size of the bucket. So in the past people used to proportion concrete in terms of 1:2:4, 1:3:6, basically 1 part of cement to 3 parts of sand to 4 parts of or 6 parts of stone, right, that is the volumetric proportioning method. So what they did was they used this bucket to measure the volume, and if you put cement in that 1 cubic foot bucket, it is approximately 45-46 kilograms. So that is why the standard measure of the cement bag is 50 kilograms. So it corresponds approximately to 1 cubic foot for volumetric proportioning. But today, with understanding of concrete technology, all of you who are trying to design concrete never do volumetric proportioning, only weight proportioning or weight batching has to be done with concrete to get the right quantity of ingredients in the concrete and to get the right properties from the concrete. Yeah, I think with that we have sort of one more question about steam instead of water in the wet process. Again, the purpose of using water is to make the slurry. You can't make a slurry with steam. Okay, the purpose of the water is to make a slurry which helps in proper mixing or blending of the ingredients. So you can't do that with steam. So you can't really change that process by changing to steam. Okay, it has to be water. Okay, I think with that we have sort of tackled most of the issues that were raised by participants in this discussion. I hope this was a useful session for you. And if you have any comments or suggestions, if you need specific questions answered, you can also access me by email. Okay, I'll again write my email on the board. So those of you who want to get in touch, who want some more questions to be answered, you are free to write to me by email and ask those questions. Okay, it's manus@iitm.ac.in. Okay, so you are free to send me your questions and interact. So thank you all for a very good session, and I hope to see you in a few days time with the second set in this module on cement composition. Thank you.